Aha! Welcome on this Friday edition of Kitchen Table Chemistry. And welcome. Today we're going to take a look at how to write an equilibrium law. Now, when it's homogeneous like this, everything is in the same phase. Writing that equilibrium law is going to look like this. K, which is again that abbreviation we use for the constant, K will be equal to, on the top, the concentration of the products, and then on the bottom, the concentration of the reactants to their coefficients. So in this reaction here, K will equal, on the top, the concentration of the ammonia, and that will be squared because that is its coefficient, over the concentration of the hydrogen, which will be to the third, to the concentration of the nitrogen, which will be to the first, because that is its coefficient. So that's how we set up a homogeneous equilibrium. Everything here is a gas, so it's all in the same phase. In a heterogeneous equilibrium, this will not be the case. So some reactions are going to have reactants and products in more than one phase, and this is called a heterogeneous reaction. For a pure liquid or solid, that ratio of amount of substance to its volume is a constant and it is omitted. And if you think about it, what is the concentration of pure water? Well, it's pure water, so it's all water, so its concentration is 100%. So it doesn't change, and we don't put it into a heterogeneous equilibrium. So looking at this reaction here, we've got a solid and a solid, which we're going to omit. So for us, K is going to equal here on the top, and I'll include them right now, the sodium carbonate times the water times the carbon dioxide on top of the sodium hydrogen carbonate squared because of the 2. We cross them off completely. Like, it doesn't matter. Don't worry about the 2, anything like that. So what K ends up equaling to, K is equal to water, its concentration. Why? Because even though it's pure water, it's in the gas phase. It's not in its native liquid phase. Times the concentration of CO2, which is again in the gas phase. So that is how we would write an equilibrium constant for this reaction. We would eliminate the solids entirely from this. Here is a second example that tends to make people uncomfortable, and that because this is a solid and this is a solid. So K initially looks like it's going to equal, on the top here, concentration of the calcium sulfate over the concentration of the calcium oxide times the concentration of the sulfur dioxide. But these two things are solids, so they're going to cancel out completely. So K, that equilibrium constant, is equal to 1 over the concentration of sulfur dioxide. Weird looking, but that's how it works. Always get rid of solids or liquids. The only thing we work with are molarities or gases, and we never interchange them. It's either all molarity or all gases. Here's some examples from the homework. And here, this had a solid in it, so we're not going to count that. So K for this, and this is from Thursday's homework, K would be equal to the concentration of the carbon monoxide, the product, squared, over the concentration of the O2. And the pure carbon is eliminated because it is a solid. Here, with this example, again, I've got a solid here and a solid there. So K will equal water times sulfur dioxide. And I don't have anything to put on the bottom of the line, so I'll just put a 1 there for the sake of putting something there. That is it. So that's how we write equilibrium constants. I think this is fairly straightforward. I've asked you to do a couple already, 14.41. I'm going to ask you to do one more like this, and then a little bit of a look at Le Chatelier's too, as I've gone through and graded your homeworks. Hopefully you're doing great, and have a great weekend, and we will return on Monday how to calculate K and what K means. Take care. Goodbye.